In this exercise, we have to sketch the graph of a function, calculating typical the local behavior of this function using derivatives, etc. Right? And then in the second part, based on the plot that we obtain of this function, we have to obtain these other two functions or represent these two functions. Right? The first one is, as you can see, the function f that we have here evaluated at the absolute value of x, right? If we substitute here the absolute value of x, well, this is a square, so it doesn't matter if you put the absolute value or not, but here you have the absolute value of x. On the other hand, we have h of x, which is the same function f, but with absolute value, so we have to represent this. Okay, so after we have this plot, we have to represent these two functions. So let's go to the first, okay, and let's analyze this. But the first thing we need to do is to figure out where the function can be calculated, so the domain of the function. And for the domain of the function, the only problem here is the logarithm. Is an absolute value here, so this is always positive or zero, so our only worry is that this is equal to zero. So the only point where the function is not defined is where this function here is zero, which is a plus or minus 1. So the domain of f is r minus 1 and negative 1. All right. Here there are vertical asymptotes. Okay, so we have two vertical asymptotes. Because the logarithm of something that goes to 0 goes to minus infinity, right? So we have vertical asymptotes at x plus or minus 1. All right? Okay. Right. There is no horizontal asymptote, right? There's no horizontal asymptote because when x goes to infinity, both these terms go to infinity or to minus infinity, so no horizontal asymptote. And about any other kind of asymptotes, well, we can say something definitely, because the logarithm of the absolute value of x squared minus 1 is negligible with respect to x, right? The reason is if you take the limit when x, of course, when x goes to 0, when x goes to infinity, when x goes to infinity, well, actually to plus or minus infinity, right? In both cases you have the same. The reason is the limit of the logarithm of this divided by x when x goes to plus or minus infinity is, well, you can calculate this using L'Hopital. So calculate the limit of the derivative of the denominator is 1. The derivative of this is just 2x over x squared minus 1, right? When x goes to plus or minus infinity. And as you can see, the degree here is 1 unit smaller than the degree here, so this is always 0. So that is negligible, which means that the function f is equal to x plus ox when x goes to plus or minus infinity. So y equal to x is an oblique asymptote, right? It's an oblique asymptote. Okay, right. Let's see. Now that we have this, we can calculate the derivative of the function, right, in order to get more information, right? So the derivative of the function can be done everywhere, right? Because all functions here are differentiable except at the point where the function itself is not defined. And it is equal to 1 plus 2x over x squared minus 1, which is x squared plus 2x minus 1, right, over x squared minus 1. Well, obviously, this derivative is not defined at plus or minus 1, right? But other than that, it is well defined everywhere else, and what we have to figure out is what is the sign of this function, right? Well, for the sign of this function, we have to solve the roots of this, and for solving the roots of this, perhaps, given that we have already these two terms, is to write this like this, right? So we have x squared plus 2x plus 1 from this factor, minus 2 is minus 1. You have this here, right? So that means that the two roots of this are, so x plus 1 is plus or minus the square root 2. So the two roots of this are minus 1 plus or minus the square root 2. All right? Okay. So we have these two factors. X squared has a positive sign. It's plus 1, the coefficient of x squared, right? So we can factor this as x plus 1 minus, well, let me put plus first, and then x plus 1 minus square root 2, right? Divided by factorizing this, well, you get x plus 1, x minus 1. All right. So there are 4 critical points to decide the sign, right? So we have the line here, okay? So we have, well, actually, you don't have to write the 0. Let's say 1 is here, negative 1 is here. These are the 2 points where one of these factors changes sign. Then we have negative 1 minus the square root 2, which will be like here. And then negative 1 plus the square root 2, which is, remember, the square root 2 is 1.4, something like that. So this is going to be 0.4, so it's going to be somewhere here. So it's negative 1 plus the square root 2. Okay. If we are here, all 4 factors are negative, so the sign of the function is going to be, of the derivative is going to be positive. Then every time we cross one of these points, one of the factors changes sign. So here we have 3 factors negative, 1 positive. Here we have 2 and 2, 1 and 3, and all 4 positive. Okay, so those are the signs of the derivative. Okay, so the function grows here, decreases here, then grows again, decreases again, and grows again, right? Remember, there's a vertical asymptote here and a vertical asymptote here. So decreasing here is to minus infinity, and from minus infinity here, right? Okay, this is pretty much all the information we need. Of course, we could analyze concavity or convexity, but I think it's something that we can pretty much infer from this. If you want to do that, you have to take the second derivative, and then you would see that the second derivative is always negative, right? Takes some time because you have to take the derivative of the rational function, but anyway, if you analyze the result is that the second derivative is a negative function, okay? Right, so what is the sketch of the plot of this function here? Well, you have something of this sort. Well, of course, you should see if there is a point where the function crosses 0, right? This point is actually 0. When x is equal to 0, then you have the logarithm of 1, which is 0, and 0 here. So f of 0 is equal to 0. Is equal to 0, right? Other than that, there must be some other point where it crosses 0, right? Because you can see from here that there is a maximum between 0 and 1, and then it decreases to minus infinity. So there should be another point, which is probably more complicated. Well, it's difficult to guess. I mean, you can only find it numerically, right? but at least we know that this must be a crossing, right? Okay, so the picture that we have of this function looks pretty much like this. Let me show you what the plot is, right? This is the plot of the function, all right? So this point here is -1 minus square root 2, okay? -1 minus square root 2, which is like -2.4, something like that, okay? It's like that. This point here is -1, this point here is 1, the two vertical asymptotes, and this point here where the maximum is -1 plus the square root 2. So this is the pattern of growing and decreasing of the function. So it grows up to here, decreases to -infinity, then it increases from -infinity, crosses at 0, and goes to the maximum, and then decreases again. Actually, we can compute what the value of the function at the 2 points -1 plus minus square root 2 is, in order to get information about whether this is positive or negative. And we would obtain that this is negative and this is positive, and then you can plot it like this, right? Even if you don't know that it crosses 0, then it decreases to -infinity and increases again, right? Okay, so this is pretty much what the function looks like. All right, so now that we have the function, we need to figure out what the other two functions look like, right? So let me just plot them here. The first one is the function of the absolute value. So let me put it like here, for instance, right? So the argument, so it's the same function, but the argument is replaced by the absolute value of the argument. So that means that in the positive side is identical. So you can see here, right, that the function is identical to this one. But in the negative side, you have a copy, just a mirror image of what you have in the positive side. So exactly this, right? Because of course, the function g of x, which is f of the absolute value of x, this function is even. Doesn't matter what f is, this function is even, because it depends only on the absolute value of x, right? So if you have it in the positive side, and in the positive side, of course, it coincides with f, then in the negative side, it's just a mirror image of this one. So that's what the function looks like. About the function h, that's the absolute value of the function. When you have the absolute value of the function, what you have to do is you keep the positive part of the function, so this arc here and this branch, and then the negative side, the negative parts become positive, right? So you have to copy them in the positive side. So when you do that, you get a function that looks like this, right? It looks sort of this, right? Okay, you can see both the arc and this branch are positive, and they are exactly the same as they are here. But the negative part becomes positive, it's identical but positive, so it's the mirror image, and so is this part here, which is in the negative side, okay? So this is the function h of x.